Welcome back to ECE 441A, 541A. I assume in a week there will be a few more seats filled up. Our exam is in a week. It's next Friday. And before that is homework assignment number 2. That's due on a Wednesday. And you also want to make sure that you understand the material in lab number 1 well enough to be able to do an exam problem on it. You don't have to turn that in. That's not due until the 1st of October, which is a week and a Monday beyond the date of exam number 1. Today what I want to do is just give you an overview of types of first order systems and a little bit of a discussion on those, and then we will pick back up where we left off last time, which was how do we identify a first order system. Then we'll look at maybe some homework hint or help on how do we look at that using different data than what we originally did in, let's say, item number 2 of the first order system ID one way. And then we'll get into lab number 1 type of system identification, which is second order underdamped system identification. Hopefully now, after last time, whenever somebody says a first order system, you may instinctively see this in your mind. Maybe you will visualize this, maybe you'll start to write it down. A first order RC circuit, that's a low pass filter, or can be viewed as a low pass filter. We have a resistor, we have a capacitor, and you should, if you have an electrical engineering background, this differential equation describing the dynamic behavior of that should be second nature at this point. You're essentially writing a KVL equation and simply using the fact that ice is involved, whatever that means. No, Eli the Iceman. So what I'm saying here is I sub C of t is related to the voltage across that capacitor by scaling it by a scale factor equaling the capacitance and differentiating the voltage across that capacitor. That I, in this case, the current through the capacitor, since we have a series circuit, is the same as the current through the resistor, and that's why we can say Ri is the same as Rc V naught prime, where here is our I of t. And then we simply say, oh, we also have to worry about the capacitor voltage to complete the Kirchhoff voltage law around that series circuit. If we solve that now for the highest powered derivative, which is just a first order derivative, we can now push everything over on the right hand side, and this particular representation of that first order differential equation, now you might be seeing a block diagram, an all integrator block diagram. If not, maybe you should. But no, it's just another way of thinking about a first order system. And the nice thing is once you understand this, now you can apply that same thought process or understanding to many, many, many other systems, and that's what I want to think about now. So that should be second nature to you, and I guess the next step should be as well, which is to find the transfer function. Finding the transfer function is simplified because we don't have to worry about initial conditions when we Laplace transform derivatives. That allows us then to immediately write down the frequency domain expression connecting the voltage of the capacitor, which we're viewing as our output voltage, and the input voltage that was supplied to that first order circuit. Then if we simply collect terms that are common to the input voltage and the output voltage and take the ratio, if we want the transfer function, we're taking the ratio of the output, whatever that is. In this case, it's the voltage across the capacitor over the input, and in this case, it was a voltage source in series with that resistor and capacitor. What you may have initially is a transfer function in pole zero form. By pole zero form, I'm meaning I factored it in such a way that if you simply found the roots of the factors, those would either be zeros or poles. In this case, we do not have any finite zeros. You might hear somebody say, well, you have a zero. It's an infinite zero. It's a zero at infinity. If you let s go to infinity, that would wipe out or drive to zero that transfer function. Anything that makes that transfer function equal zero is viewed as a zero, but typically when we say zeros, we're by default usually meaning finite zeros. There is no s in the numerator of that transfer function, so there's no finite value of s that causes that transfer function to vanish. You have no finite zeros. You do have a pole. It's first order. You should expect one pole. But what we are going to be doing today is trying to identify that transfer function. And the way that we will identify it, it might be more straightforward to do that by converting that transfer function into time constant form. Or what that means is normalizing that constant coefficient in the denominators factors to 1. And then what's multiplying the s, in this case a first order, that tau is our time constant, and whatever is floating upstairs is our DC gain, or the gain of the transfer function. The DC gain, the gain at low frequencies, in this particular case is that transfer function evaluated at s equals 0. If we plug in s equals 0, what do we get on the right-hand side? 1. So that means whatever we put in as an input voltage, eventually, if this is a stable system, which it is, it's a passive circuit, it's a stable system, your output, you're expecting it to go to exactly what you put in as the input voltage. You put in 7, the output voltage will be 7 across that capacitor in steady state, or at infinity. And what's infinity? It's not very long, actually. It's 5 time constants. So anytime you get beyond 5 time constants, effectively you're at infinity. So when is infinity not infinity? In this class, when it's equal to 5 tau or 4 tau, depending on how we define our settling time. Is it clear then what I've done for this first order system? We've modeled it in the time domain. You could have, if you didn't want to think about an all integrator block diagram or a differential equation, you could have immediately moved into the frequency domain and drawn an S domain circuit. And then you would have Laplace transformed little v sub I, giving you capital V sub I. You would have had to worry about the impedance of your capacitor, which is 1 over SC. What's the impedance of a resistor? The same in the time domain and the frequency domain. It's R. And do the analysis with algebra, and now you have the same transfer function. That's something that you can, I hope, hang your hat on. The analysis of a first order. Any time you go into a interview and somebody says, well, tell me a little bit about electrical engineering, you could spend 30 minutes talking about a first order circuit, and they would just be so impressed. I hope. Or you could start drawing cars. I love my car here. It's Fred Flintstone almost. But now you can also have a first order system from a vehicle, where here we're interested in the velocity of that vehicle, and the input is shown by that U that's pushing the car forward, the force, the applied force. U is the input. The position and velocity I've drawn, I've basically said, okay, here's where I'm going to assume is 0, and then I'm assuming there's some velocity damping in that system proportional to the velocity, and that's where this BV force is coming from. So we have a force due to the applied force, input, U. We have some force due to the speed of the vehicle. You could think of that as wind resistance. And what else do we have if we're trying to model the dynamic behavior of that system, that vehicle? Now you can look to how I've conceptualized the car as a block. It's now a mass, and maybe I should have put a mass inside the block. And now if you wanted to try to push that block, that mass, in the positive x direction, you're going to have an inertial force that opposes that. Now we have the three forces, and the inertial force is ma, or mv prime, m times the first derivative of the velocity, plus the damping, bv. Those are both going to the left, and the applied force is going to the right. I'm setting those equal, and in the time domain I now have a first order differential equation in terms of velocity of that vehicle. Again, we could find the transfer function by Laplace transforming that differential equation, and then it's really not quite in pole zero form because we have an m that's multiplying the s, but you could factor out the m if you wanted to and put it in pole zero form. Or, consistent with what we want to talk about today, really what we're trying to show is that all of these first order systems boil down to an alpha over tau s plus 1. And we want to be able to find alpha and tau by system identification strategies. So somebody now says, oh, I have a vehicle. I want you to tell me the dynamic behavior of that vehicle. Well, you don't necessarily have to know M and B. If they give you some data, you can now find the DC gain and the time constant of that mechanical system. Just like in the RC circuit, you wouldn't have to be told the R and the C if they give you physical data and they say, give me a transfer function that models this between the input voltage and the capacitor voltage. In this case, tau is mass over the damping, V. You could have a thermal system. This room, for example, maybe if we modeled it as a single temperature, how does that change after you put 100 watt bulbs in here? That's what we are. We're all just 100 watts on average. As we go, that's what it takes to keep us powered, is 100 watts. That's why you get this 2,000 calories per day as the nominal. If you kind of back that out, you'll find that that translates into us just glowing like a 100-watt bulb all the time. So now if you wondered why did the room heat up when we put 100 bodies in it, live bodies, that's the reason. That's why it takes some conditioning to maybe stabilize that temperature in the room. Fluid in a tank, similar. If you have something flowing into a tank, let's say one source, Now you're pouring water in and the water just goes up, kind of like you're charging that capacitor. Again, a first order system. You've also, I think, didn't you have a homework problem on a DC motor? Or maybe not. Maybe it was just in the notes. But you can also model a DC motor as a first order system if you were interested in the transfer function between the applied voltage to the terminals of that motor and the rotational velocity of that motor. Not its angle, but its speed of rotation, the omega. And this is what we derived in the notes earlier this semester. And it's connecting the motor constant, the armature resistance, the rotational inertia of the motor, and the damping in the motor. But really, if you look at that, how many S's, or what power of S is in the denominator? 1. This is a first order system. And we can now factor out the constant in the denominator, the B R sub A plus K sub M squared. That ugly mess we can factor out and normalize the constant coefficient to equal 1 so that we can put this in a time constant form. The alpha now is some mess, ugly mess. The tau is some ugly mess, but if we don't need to know what those are, if we just need to know alpha and tau, we can find a model for this DC motor. And that's all we might need to know to control it, is what's its DC gain, in this case in time constant form, that's alpha, and what's its time constant tau. Questions on those systems, or how we now essentially made them all look the same? You give me a DC motor, you give me an RC circuit, you give me a thermal system, I'll give you a first order system. Now do you see how you can impress your interviewer with even more verbiage? But sir or ma'am, this first order system can model a plethora of systems. We're here to impress, right? Your interviewer. So there is our first order system of the DC motor. Let's now figure out how to identify or find that alpha and tau. Let's do first order system identification by hitting, by applying, by exciting, you may hear me say all of these, this system with a constant input. And it may not be a unit step. In the lab, you're hitting that mass with a reference input. You're commanding it to go so far. How far are we telling it to go? Anybody done the lab yet? How far did we tell it to go? 2,000 counts? I may be not remembering, but you're telling it, you're saying go so far. And maybe it only goes up to 1,200. Well, that kind of tells you something about its DC gain. And how quickly did it get there? What we want to do now is figure out how do we go ahead and find this G of S, which we've learned can be thought of as an alpha over tau S plus 1. If that's our system, G of S, and we apply a constant, what kind of a time response trajectory are you expecting to see? And I'm assuming you've all already run home between last time and today and studied up your differential equations. Now everybody hides their eyes, right? They don't want to make eye contact with the professor. I don't have my glasses on, so it doesn't matter. You can look at me and smile or frown. No, please, the smile is what I would prefer. I can actually see smiles. Maybe that's about all I can see. All right. I have a first order filter on, so when I see your face, the corners of your mouth just naturally go up, right? Okay, help me here. Where are we going with this? What's the trajectory look like if I apply a constant input to a first order system? No one wants to help me? All right, it's a Friday. I'm on my own. At least give me a cheer or something. Yeah. I guess I didn't give you the A, B, C, D, did I? Anyway. Here's y of t, and it's not supposed to be so jagged at the end. You guys threw me off with that cheer. Let me try again. I'm sure it won't be any better. But something like that. And what are we looking at? Now we might try to find at what time do we get within 1% of where we finally reach. And maybe we call this y final value, and maybe we'll even give it another variable descriptor, a sub 1. Here, basically, all we need, if this is what we're given, if somebody hands us this trajectory and they tell us what they applied at the input, if they said, oh, I put in a constant a, not a sub 1, a constant a, and we measure an a1 eventually, and we say, oh, we made it to a sub 1 close enough, within 1% at time t sub s, our settling time. Do you remember what, and I've been saying this occasionally, how long is t sub s in terms of time constants? Depends on what we're calling our settling time. If we say a 1% settling time, then this is approximately 5 of those time constants. What I'm meaning is typically if we wrote this mode of response, it would have a shape e to the minus t over tau in terms of how it's approaching its final value. And if we plugged in a time of 5 tau, if we plugged in a capital T sub s into that expression, then this becomes e of minus 5 tau over tau. The taus cancel, and we have e to the minus 5. And I'm sure you all have that memorized. But if this is corresponding, if this T sub s is a 1% settling time, then you would expect e to the minus 5 to be close to 0.01. It's actually a little less than that. That's why it's approximately 5 tau. But this is 0.006, what is it, 7, let's say. But that's close enough. I know that makes you feel maybe a little nervous, but a lot of this is going to be fairly hand-wavy values. I mean, when do you find 1% of the final value? That may be a little bit subjective as far as where you're drawing that line. But now that we have that information, can we find alpha and tau? So let's go ahead and assume a constant input that we're applying to the system. Let's say capital U of S, is now A over S. So it's not necessarily a unit step. It's not necessarily 1 over S. We don't have to restrict our analysis to just applying a unit step. But once we have the Laplace transform of our input, now we can find an expression for the Laplace transform of our output. One, because we haven't fed any signals back, this is a straightforward open loop analysis. Y of S is simply the product of G of S and U of S. Or Y of S now, in terms of how we have generically parameterized the transfer function, this is alpha over tau S plus 1. And U of S, we said, was A over S. Now, if you're in that interview, you could say, well, we could just apply the final value theorem and get a connection between these parameters and A sub 1, or Y sub FV. And they'll go, oh, you remember your final value theorem? And you'll say, of course. I had Tharp for 320, or if you say no, then don't answer who you had for a class, okay? Don't go that far. Just say, I don't know that I remember the final value theorem. What is the final value theorem? That's where the output is going as t goes off to infinity. But the final value theorem is nice because now we can apply it to the S-domain version of the expression for y. And that is that we can now say that, oh, that's the same or equal to the limit as s goes to 0 of s capital Y of s. And now we can say, oh, that's the limit as s goes to 0 of s alpha tau s plus 1 A over S those s's cancel. We let s go to 0, and what do we end up with? Is the denominator well behaved as we let s go to 0? Yes, we just have it going to 1, and what's left is A times alpha. And that's equal to either y final value, or if we called it A1 before, that's equal to A1, our final value of this first order trajectory. Question? So where did this come from? That's my final value theorem. So the question, I think, was why can I equate these two sides of this expression? So the limit as t goes to infinity of y of t is equal to the limit as s goes to 0 of sy of s. Tharp should have explained that in 320, maybe. Maybe no one had me for 320. Most of you then were lucky if you didn't have me for 320. All right, so now that's our relation. Did that answer your question? So that's, I'm not going to derive that. I'm barely going to get through the material I'm hoping to get through, but you can go back and look up the final value theorem and see why that's true. Now we can, what are we trying to find? We measured A sub 1, the final value. We knew how big of an input we applied to the system. That was A. We were trying to find the DC gain, or the alpha constant, in our G of S transfer function. And now we have it. Now we can solve for the DC gain. That's the ratio of where we end up to what we put in terms of constant. And I think I've already said this several times, but the DC gain of our system the way we parameterized it is simply alpha. And look what happens. Well, the DC gain, what happens in the steady state if we have a stable system? We simply scale what we put in, A, by the DC gain, alpha. And that takes us to what we measure, which was A sub 1. So now we have one of the two unknowns in our transfer function g of s. We found alpha. And from our 1% settling time, relationship, we find where we end up, and we say, when did we get within 1% of that final value? And that now is what we're calling t sub s, our settling time, and we said that we are going to agree is 5 tau. If you now go in and measure that t sub s, you now have indirectly found the time constant tau. We can solve that for tau. And now we have identified our system. And essentially, we found that by saying, where did you get to, and when did you get there? And we use that information to find alpha and tau. Obviously, you have to be told how hard did you hit the system. We hit it with an A. Now, on the test or on the homework, it's probably not going to be quite like that, is it? You can just assume that a curve might be thrown at you, or it might be slightly different. So let's look at this a little differently as far as system identification. Let's examine first order system ID more generally. And now I'm going to use an omega sub s, so it's sort of begging the idea that, oh, maybe now his first order system is a DC motor. And that's maybe what you're going to be dealing with on your homework problem, a DC motor. But again, we're assuming now if it's first order, it can be modeled as alpha over tau s plus 1. There's our transfer function, and if somebody gave that to you and asked you on an exam, what's the order of that transfer function, I hope you bubble in 1 or first. Not second, not third. That won't be on my test, but it might have been on somebody else's. So now what we want to do, our objective, is to actually find, again, these unknowns, alpha and tau. And we know omega s is g of s v of s, and let's just assume that the applied voltage to that motor, again, is a constant value. You apply a constant voltage, maybe 2 volts, and now bzzz, your DC motor spins and it reaches a steady state rotational velocity. And we want to use that information to identify it. So here's a constant input equaling A. And now maybe somebody says, well, what's the expression, general expression for omega of t? And you simply have to pull out your cursive writing and say, oh, it's the script L inverse. It's the inverse Laplace transform of omega of s. And maybe they'll stop asking you questions at that point. But if not, you may have to proceed, go a little further. So now we have the inverse Laplace transform of alpha A over S tau S plus 1. Just plugging in G of S and A of S. And here we've parameterized that G of S to be in time constant form. That's the alpha over tau S plus 1, and the input, V of S, is the capital A over S. But if you've now been doing inverse Laplace transforming by partial fraction expansion, you probably didn't do it in a time constant form. You probably had it in pole zero form, so that you could then put everything over these denominator polynomials that were representative of the poles of your system. If that's the case, now let's start to rewrite that expression. So let me pull out the tau and put it into a pole zero form in the denominator. Or I now have alpha A, and I have S tau. Now I have S plus 1 over tau. And now you can see the relationship between the pole and the time constant. They're reciprocally related. And if I pull that constant tau upstairs just to make it a little cleaner, this now is in a more conventional pole zero form. Of an expression. And now, once we have it in that form, it should be instinctive to write the partial fraction expansion. You have two factors, and you'll break your product into those two factors. A sum of two terms, B1 is over S, and let's say B2 is over S plus 1 over tau. Are we okay with that? That's just a partial fraction expansion. We can now find the b's. We multiply everything by s and let s go to 0. And that will isolate B1. So B1 now, if we do that in that curly bracketed expression, if we multiply that by s, the s in the denominator goes away, and we evaluate that at that location where that factor vanished, or at s equal to 0, and we're left with b sub 1's value. B sub 1 is now alpha A over tau. That was in the numerator, and 1 over tau in the denominator. Or the taus cancel, and we end up with B1 is alpha A. Or A alpha. B2, we multiply through all terms by what's underneath B sub 2, and that's this factor s plus 1 over tau. And we set s equal to the value that causes that factor to vanish, which is s equal to minus 1 over tau. We do that. The numerator hasn't changed any, but now we're left with s downstairs, and we said we replace s with whatever it was that caused that factor underneath b sub 2 to vanish, which was minus 1 over tau. And that looks similar, it's just now we have a negative sign. So that now b sub 2 is minus a alpha. Now can you give me the expression for omega sub t, omega of t? That's just b1 plus b2 e to the minus t over tau for t greater than or equal to 0. Or plugging in the b expressions parameterized in a and alpha, we now can say, oh, we had an a alpha common to all of those. And that's now our parameterized expression for this first order system in terms of an input amplitude of a DC gain of alpha, and a time constant of tau of a first order system. Now what? What do we know from this parameterized form of omega t? And that's the velocity of the shaft that's spinning if this is a DC motor. And in the textbook they may say, oh, I did an experiment and I actually applied, I'm not remembering the numbers, 4 volts to this DC motor. And at a certain time, at 2 seconds, it was spinning at 35 RPM. And then I dropped my watch, and the next time I looked up, it had reached steady state. I don't know when it reached steady state, but it got to steady state, so I don't know when it settled. But I do know at maybe 2 seconds it was going at 35 RPM, and then eventually it reached 80 RPM. Do I have to do the experiment over so that I can put it in the form that we just talked about before? No, we can figure it out from what we have, right? We just need to find alpha and tau. But we can always fall back on this, right? We know that it looks like this. Here's omega of t. And what do we actually know? Well, somebody was paying attention and found that at t1 it was spinning at omega 1. And then they went for coffee or something, and then all of a sudden they come back and they tell us what it's finally spinning at. It's omega final value. And they didn't figure out when it reached that, but they did give you the final value of omega. So we were given this, that, and that. And we're also assuming that they knew what they applied to the terminals of the DC motor. So we were given a constant input of A. So what I'm saying is we weren't given T sub S like we were before. Oh, sorry. We didn't get that. So we don't know what the 1% settling time is. And maybe I should say that this textbook probably throws out the 1% and they use the 2%. So if you like 2% milk versus... So the textbook usually uses a 2% settling time. And that's now approximated by 4 tau instead of 5 tau. So you'll see different sources talking about a settling time of 4 tau or 5 tau. Now you know that that just corresponds to either when you get into the 2% tube or the 1% tube of your final value. And you obviously get into the 2% tube sooner than you get into the 1% tube. So this is 4 tau instead of 5 tau, and this now is 4 tau is e to the minus 4, which is approximately 0.02, but it's not quite 0.02. This is 0.018. So maybe that's closer to 2% than the e to the minus 5 was to 1%. Anyway, the textbook usually uses 2% settling time. What do we know about the final value? Can we use it? Well, we have an explicit expression for omega t as a function of time. So we really don't even need to apply the final value. We just need to use that time domain formula. That was A alpha times 1 minus e to the minus t over tau. And what does that become, or what does that equal when you let t go to infinity? The second term in that bracket vanishes and we're left with A alpha. So now if we called this A1 or if we called it omega sub final value, we have alpha. Now what? So now we have one of the two parameters. Which parameter do we have? Now with this information, could you answer some questions that somebody might supply you? They say, oh, I put in 4 volts. What's my final velocity? Now you know how to calculate it because you've got the DC gain. You can't tell them how quick you get there. You don't know tau yet. But you can now use this to supply them with a final velocity or a final rotational speed given any input voltage. You now know the DC gain. So maybe you only have half of the model, but that's a good half so far. If they don't care, and electrical things don't take very long. So if they're patient, you've given them the answer and they don't have to wait very long to get there. But how do we find tau? Five tau. Do we know 5 tau? We dropped our watch and we forgot to see exactly when it reached 1% or 2%, didn't we? So we don't have that. But somebody has given us some generic T1 and an omega 1. And we have the expression for omega of t as a function of t and all of our unknown parameters. And we found most of those. So let's see what we have. We can say, oh, omega of t sub 1 is now equal to omega 1. That we were given. And we were told that that was measured at a time of t sub 1. So this was given, this was given, this was given. That's all I can say is given, given, taking roll. Given, all right. What's alpha? We found that. There's only one unknown in that remaining formula. We can solve now. So if we call this star, we can say solve star for tau. And now we know how quickly we made it to our final value. We'll pick up next time with second order, but you might look at the Lab 1 materials, demo, video, notes, etc., so that it makes a little bit more sense what we're talking about next time.